Hello everyone. Let us now look at the transition rates. So, we looked at the transition earlier, but let us look at what are all the rate constants associated with spontaneous emission, stimulated emission and absorption, and how these rates are going to affect our light emission and the characteristics of light emission as well. So, let us look at that. So, the transition rates depend on the energy states that we have and associated rate constants, right. So, the spectral distribution of any field. So, when you talk about light generation, right, of a certain frequency, we should also understand what is the energy density that is associated with this, or the spectral density that we have, or the spectral distribution across by the radiating field. So, so the transition rate, it's actually is induced by this spectral distribution of optical radiation, right, and the spectral characteristic of the resonant transitions as well, right. So, let us look at the spectral distribution of a field, right. So, the spectral distribution of field is given by this. There is the spectral energy density is given by some u of nu, let us say. So, the energy density of the radiating field per unit frequency, that is what this spectral energy density is. This is nothing but the energy density of the optical radiation per unit frequency, right, at the interval of frequency or whatever, right. So, this is how we define it. The total energy is nothing but an integral of this, right. So, total energy of the radiation is given, let us say it is u, it is integral of what we have here. So, that is the total energy that we have. So, that is important to note that when we talk about the total power carried by an optical wave or optical beam, right, we have to qualify that with respect to the frequency or the wavelength that you have, right. So, the power could be couple of watts, right. So, the light bulb or whatever that we have, right, the energy that is put out can be measured as a total energy of radiation, right. So, it could be a few milliwatts, let us say. So, but then the spectral energy spectral density is nothing but the energy of individual frequencies or individual wavelengths. Okay. So, here let us say if you want to put the spectral intensity, so the spectral intensity is given by C over n u times nu. So, now I want the total intensity will be equal to the, again we are going to integrate this over the frequency range. So, the intensity over that frequency range will give you the total intensity I. Okay. So, it is important to differentiate between the total intensity that we have and also your spectral intensity. Okay. So, the way that you can visualize this is, if you have a wavelength, it will have a certain spectrum, right, and when you measure the power or the total power, you have to integrate this whole region. So, this whole region integrated will be in some watts, let us say some watt power. But then the energy spectrum or the spectral energy here is in this particular delta lambda, let us say. So, how much of power within this? So, this will be some milliwatts. Okay. So, the total power is different from the spectral intensity or the spectral energy that this particular wave carries. Okay. So, that is the reason why the spectral relation is very important to understand. So, let us look at the transition rate. So, all this emission happens through transition, okay, between the two levels that we already know of. So, let us take this the two levels here. So, you have N1 and you have N2 and you have transition from here. So, we call this as transition rate W12, which is equal to B12 u times nu, right. So, let me only write this so that I can write it in a separate way, and then you can go from top to down. So, I will pick a different color. So, you can go from top down, that is W21, and then you could have another transition, that is W spontaneous. So, W12, right, is our upward transition. This is upward transition W12, that is from level 1 to level 2, right, and that is given by B12. This is the absorption parameter u times nu, right, or in other form as a function of frequency B12 u nu and G nu dV d nu. Okay. This is per second. Okay. So, this is the transition rate, right. So, that means this will be per second. The same way you have two downward transitions, right. So, let us look at the downward transition. So, the downward transition we have W21 nu d nu is nothing but B21 u nu G nu d nu. Alright. So, this is our stimulated emission. So, this is our stimulated downward stimulated, and then we have downward spontaneous. And that is given by W spontaneous frequency nu, which is nothing but A21, which is something that we already saw, G nu d nu. All right. So, let me write it closer. A21 G nu. So, this is our spontaneous emission, that is independent of the energy density of the radiation, right. So, this is the transition function here is the line shape that we have for this. All right. So, the A and B here are nothing but the Einstein coefficient, right. All right. So, now we have this process defined, right. We have upward transition and we have two downward transition. So, the spontaneous emission, right, there is characterized by our emission coefficient A21, right. So, this A21 is the spontaneous transition here. So, this is characterized by A21 and B21 is characterizing our stimulated emission, and then B12 is induced absorption. We can call this as induced absorption or absorption. Okay. So, these are all the three different processes that we have, and we want to look at the transition rates, right. So, how quickly this the transition happens. So, how do we do that? The transition rates are the total induced transition rates are nothing but the integral of this. So, we have defined this as a function of frequency, right. So, we want to understand what is the total rate. So, that means we need to integrate this over the frequency, right. So, your total total induced transition rate is nothing but W12, which is integrating it with all the frequencies that we have within this, right, and that would result in B2 B12 0 to infinity, nothing but your line function here. Okay. Similarly, we can do this for W21 as well. Okay. So, W21 nu dV, which is B21 0 to infinity. So, now the total spontaneous emission, now this is total induced transition. So, induced transition you should understand underline here. So, what is the total spontaneous emission? The spontaneous emission rate here, that is A, that is WSP, which is given by integral WSP nu d nu, which is A21, as simple as that. Okay. So, these are all the factors that determine your transition rates between the different levels here, right. So, higher level and lower level. So, the induced and the spontaneous transition rates are now directly proportional to one another, right. So, this is coming from our the line shape that we have, and this could be related through our the line shape itself, and that is coming from our spectral energy density, right, of any radiation, for example, and that is given by the Planck formula, the spectral energy density. The spectral energy density of black body radiation, which we could use here, at temperature T, is given by this simple formula that we all know of, right, h nu kBT minus 1. So, here Kb is your Boltzmann constant, right. So, the rest of the things are straightforward here, where n is the refractive index, c is the speed of light here, and nu is the frequency that you have. So, your kBT here is at room temperature 300 Kelvin is about 26 milli electron volts that you could use in here. So, based on this we could clearly see what are all the different contributing factors here, right. So, one is the photon density of states in the medium. So, this factor that let me chalk out this factor is the photon density of states in the medium, and this is nothing but your photon energy. And this factor that we have is nothing but the photon probability of occupancy, right. So, this is photon probability of occupancy, right. That is giving you the states. This is nothing but the average number of photons in each state, right. So, given by Bose-Einstein distribution, right. So, this is how you could deconvolute what we have from our Planck's formula here, right. So, we know all this transition, but let us look at the rate relation between the two states now. So, we want to at the end we want to derive or relate these time constants and also find the intensity and the cross section that we are going to get. Okay. So, for that let us assume that N1 and N2 are the states in level 1 and level 2, right. So, now let us look at these two levels, and we have N1 and N2, right. And we also know that your upward transition and downward transition. So, let us say the two downward transitions have got W21 and WSP. So, now the emission, right. So, let us say the downward transition is given by just the downward transition is nothing but N2 times W21, okay, times nu plus N2 WSP nu, right. In other words, N2 is nothing but W21 nu plus WSP nu. So, this is our downward transition. So, let us look at the upward transition. So, upward transition is given by W12, right. So, from N1 to N2, and that upward transition is now given by N1 W12 nu d nu, right. So, this is our upward and downward transition that we have. So, we need to look at the equilibrium, right, a thermal equilibrium, right. These two should be equal, right. So, at thermal equilibrium, right, your N2 W21 nu plus WSP nu should be equal to N1 W12 nu, right. So, this is in the thermal equilibrium. So, the steady state population now. So, what is the steady state population now between this N1 and N2? You could easily get this from this ratio there. So, that is W21 nu divided by W21, sorry, W12 in this case, W12 nu plus W spontaneous here. And we also know the coefficients here. We can remove this rates and then put the coefficients that we know divided by B21 u of nu plus A21. So, this is the steady state equilibrium condition, right. So, now since this transition that happens, right, could have degenerate states here, right. So, whatever the transition that we are talking about from different positions here, these are all degenerate states here anyways, right. So, one could write this as a degenerate states, right, looking at the Boltzmann distribution that we all know. So, the Boltzmann distribution gives you this relationship from the degenerate modes minus h nu divided by kBT. So now so the G is nothing but the degeneracy factor that you have, and based on this relation we could write our energy density. So based on this we could write energy density U of nu as A21 divided by B21 divided by G1 B12 G2 B21 to e to the power h nu divided by k bt minus 1. So this is our modified energy density, right, when you are looking at the transition rates, right. So this gives us how the transition is going to be, and you can clearly see this transition that we see as a the induced process, the absorption and stimulated emission process is directly related to the spontaneous emission rates. Okay, so there is no escaping from the spontaneous emission here. All right. So what else do we want to understand? So we want to understand what is the capture cross section or emission cross section of this. Okay. So the spontaneous emission factor we all know, but let us try to probe a little bit more on this W factor. Okay. So we had this W21 and W12. So what are all those? So those are all transition rates, but we haven't converted those transition rates into something that that is measurable or something that we can relate to the material property. However, A21 we already know. Okay. So A21 is nothing but, we all know A21 is nothing but the transition that we already know of, that is 1 by the dk, right. So this is something we know. So we want to also understand how this the other factors, the W21 and W12 factors are. From that you can also calculate your B factors. So the transition rate now W21 can be written as C cube divided by 8 pi n cube h nu, the spontaneous one, divided by u nu g nu, all right, which is equal to C cube divided by 8 pi n cube h nu tau s p into okay. So the W12, so function of nu, is G2 divided by G1 W21 times nu. So this is the transition rate of W21 that you have, that is going from the excited state to the ground state, and W12 which is our ground state to excited state. So now we have written the rate constant going from ground state to the higher state, and also the higher state to the ground state, all right. So now we can express this the transition probability as a function of optical radiation now. So now we can write this as a function of intensity here. So intensity of this over this is nothing but our photon flux times your cross section. So this is what we call emission cross section. Right? And similarly we can write W12 which is our absorption cross section. So, what is this absorption cross section and emission cross section? They are related though. So, they are nothing but what we already saw, sigma spontaneous. So, this is our emission cross section, and our absorption cross section is given by C G2 shared by G1 epsilon 2 1 or G2 divided by G1 epsilon E times nu. Alright. So, this is the emission and absorption factors, and we already know the G here, right. So, the line shape that we already saw, right. I am just going to write this again from our earlier equation, which is nu minus nu 2 1 square plus the band width here, right. So, the peak of this event, so where is the peak that appears in the line width? So, the peak line width, the peak of the line width, right. So, where will it appear? So, when the denominator is the lowest, right. So, that means you are in resonance. So, nu should be equal to nu to 1, right. So, if that is the case, then your nu to 1, right. So, when nu is nu to 1, that is where you have the peak of this resonance is going to be there, and the peak value of emission cross section, right. The peak value of emission cross section, that is given by, you just substitute this. So, that is all I am going to do. I am going to substitute this there, and you will get so this is our peak value of the cross section at the central wavelength lambda. So, at this particular wavelength in the spectrum. So, what is your peak emission cross section? So, these are all the factors that are related to the material now. So, we know that this is what you get, right, and more importantly we can also do the emission cross section in this case and also calculate it from here. So, this is something we saw, and we know where the peak is, and by substituting this we got the actual emission cross section. So, this is something that we can actually measure and then calculate, right. So, based on this calculation we can find out how much is our emission cross section. So, for example, you know, I'll give you a very simple example here for a material, right. So, let us take what is the material. If you look, let us say helium neon laser, so which is something that we all know, right. Your wavelength of emission here is going to be, let us say 632 nanometers, right, and the peak here, peak, right, at this wavelength is about 3 into 10 to the power of minus 17 meter square, right. So, this is your peak cross section, right, and the spectral width this one is about 1.5 gigahertz, right, that results in, and the spontaneous lifetime is 300 nanoseconds is what we have, right, and the stimulated one, right, the stimulated one, let us say the stimulated one is about 30 nanosecond. So, you can see here the stimulated lifetime, right, is rather small compared to the spontaneous lifetime, which is natural. The spontaneous lifetime is natural lifetime, but the stimulated one is from an external one, which can be always be shorter. So, this is what is going to dictate your line width, right. So, whatever comes on top is something that that you have to live with. Okay. So, similarly you can find these kind of parameters for various laser materials. So, this is for helium, right, helium neon. So, you could also have for semiconductors, right. So, for a semiconductor the values are pretty broad, right. So, your wavelength here could be anywhere between 370 nanometer to about 1550 or 1650 nanometers, right. So, your capture cross section here, the peak cross section is going to be much larger. So, 1 to 5 10 to the power of minus 20, right. So, this is rather small cross section area, and that is the reason why you have the spectral width which is also pretty large. Okay. And this results in our spontaneous lifetime. If it is larger, then your lifetime has to be smaller. So, you are talking about nanoseconds, and your stimulated process is also in nanosecond. Okay. So, you can see here the time constants. So, semiconductors are much better in handling the spontaneous decay rate, so that we could have a better spectrum when it comes to the generation of wavelengths that we have. Okay. So, with that we have now understood the transition, different transitions we have, and how to calculate these line widths, right, and what is the implication of this transition rates on our final line width. Okay. So, in summary, it's the line width that is important, and also your capture cross section. Your capture cross section make sure that your capture cross section has to be larger, right, while your bandwidth or the line width that is required to be shorter. So, this is the relation that you have. I mean, even when you look at the spontaneous lifetime, if you have a longer lifetime, your capture cross section will be smaller, and that is the reason why in a semiconductor your spontaneous emission rate is in few nanoseconds. Okay. While in gas lasers and other things it is much larger, right, in few tens or hundreds of nanoseconds, which makes the capture cross section reasonably large. So, these are all the relations that you could find out from a different material, and then take a call on whether this material is suitable for your kind of application when it comes to the spectral shape and the emission rates and so on. Okay. So, going forward in the next class we will look at even deeper into this absorption and emission. So, we understand all this dynamics inside, but now we need to generate photons, and this the generated photons should act as an amplifier to an incoming signal. So, this means you need to have absorption in the material and then emission in the material in a stimulated fashion. So, let us look at that in the next class. Thank you for listening.